for those of you that may have grabbed the slideshows yesterday, I actually changed them from yesterday, so you might want to go back to Schoology if you're taking notes on the slideshow itself. So this won't match what you got yesterday. It will, because I changed it this morning. Okay? Here we go. You can tell automatically it's going to be important because it's called the fundamental theorem of calculus.
And there's a puppy on it.
What's the matter? And it has a puppy on it, right? Thank you for observing. Most people won't even know. The reason I put the puppy up there is I'm just seeing if anybody pays attention to the first slide on the slideshow, and obviously Molly does. Good job, brown notice. Okay, two parts of the fundamental theorem of calculus. One is more practical, the other one is more theoretical. So we'll get to the practical one first. We want to be able to take a derivative. I hate teaching in this situation, but anyways, we're going to make the best of it. Where was I? Allows us to find a definite integral for any function at any point in time, as opposed to what we did 2 days ago, where it was always a rectangle, a triangle, a trapezoid, a semicircle, etc., etc. Okay, so we are going to talk about the fundamental theorem of calculus. We're going to talk about the second fundamental theorem of calculus, okay, or part 2 that comes later. We're going to talk about the concept of an integral being an area accumulator. That's going to be very helpful when we get into problems that involve more theoretical ideas. Okay? And then we're going to show you a little trick on your calculator that will save you a ton of work. Okay? To the point where on the calculator portion of the AP test, you're never going to do a definite integral by hand. Okay, yeah, it's pretty cool. And then for today, strive to be more positive. Okay. All right, here it is. Fundamental theorem of calculus. If I want to find the definite integral, remember we defined the definite integral as the area under the curve. So for instance, I'm looking for the area under the function of f of x from a to b. Then I can find that by doing 3 simple things. Number 1, find the antiderivative. By now you should all be pros at that. Number 2, plug in b. Number 3, plug in a. Done. Well, technically 4, because then you got to subtract. Forgot about that. Oh, that's 4 things. Yeah, just that kind of important thing. And, right, and then take the square root. Twice. Okay. Remember when we first introduced antiderivatives, we were operating up until that point with the idea of lowercase f of x, f prime of x, f double prime of x, f triple prime of x, and then we said if we go backwards one more, we're going to call that capital F. Okay, so what that's saying is, if I want to find the area under the curve, I need to take the antiderivative of f to get capital F. I plug in the starting value. Sorry, I plug in the ending value. I plug in the starting value, subtract the 2, we're done. Okay? Now, where does that come from? You're going to have to trust me on this one, because I'm not going to spend the time to show you the derivation of the fundamental theorem of calculus. Nobody would enjoy that, myself included. So we're just going to start doing it. This is the practical application of how to find that definite integral. Okay? It's so important it spins in a circle. Okay, so we'll do this. Now, that's not going to give us a rectangle, triangle, semicircle, trapezoid, something geometric. It's a nice pretty curve. You all know what x cubed looks like. Sorry. And we want to be able to find the area under that function of x cubed. Okay. So again, 4 things. Take the antiderivative. Faith, what's the antiderivative of x cubed?
X to the 4th, and then 1/4 x to the 4th.
Yes? How'd you do?
Plus c.
Oh, good. No plus c anymore. Okay, because remember, this is an area. Plus c's are involved when we're doing indefinite integrals because we get a family of answers. This is going to be a numerical number. Ooh, I got a out of Molly. Vector.
You can do plus c, you'll just cancel out.
I'm not going to comment on that until later. But astute observation. Okay. Whoops. I know how to work my own board. Okay, so Faith said 1/4 x to the 4th.
Yes.
Now let's talk about some notation since we're doing a definite integral. 1/4 x to the 4th, then we bring a nice big vertical segment in there. put a 0 down at the bottom, put a 3 at the top. This is how you show work. On a quiz, a test, or the AP test, the reader wants to be able to see if you have the wrong answer, where did you make a mistake? Did you make a mistake because you can't do math? Or did you make a mistake because you took the antiderivative wrong? Those two things are important. So this is how we demonstrate, yeah, I took the antiderivative of that. I know it's right. And then I apply the fundamental theorem of calculus, plug in 3, whoops, plug in 0, and simplify. 3 to the 4th, I believe, is 81. Yes? Well, by the way, you're going to need your calculators. If you don't have it out,
You're right.
it is 81.
Yes.
And of course, we all know that 0 to the 4th is 0, so that term disappears. This is no longer an approximation. That's exactly the area of that curvy region. We don't have to draw rectangles. We don't have to talk about the theory of making the rectangle smaller or increasing the number of rectangles. It does it for us. Pregunta, señor?
Would it be 84 over 16?
No.
Oh, wait, no, wait, no.
It's just the 3 to the 3 of the 4th bar. Okay. Question?
Do we ever have to write like units squared or anything?
No. Well, hold on. I sometimes have problems with like always or never. For the most part, the answer to your question is no. But later on, we'll get into some problems where you will need units, but not
Is
here.
it incorrect if we write units squared?
It's not needed.
So we get points off.
Am I waiting, or
Yeah, would you get points off when it's like unit squared?
why would you if you don't need to?
I just thought it was supposed to.
Yeah.
I mean, no. I mean, it would be like throwing a smiley face at it.
Oh, okay.
It's not needed. You could do it.
No.
Right. Okay. We good? Any problems? Good. Let's look at some more examples. You solve that one, please.
Oh, I got it. Do I though? Alright.
Helpful hint, I would recommend rewriting it first.
Yeah.
Sorry. I'm trying a new flavor of Monster, and it tastes like a watermelon jelly rancher. It's making me sick. But I continue to drink it like an idiot. That's what that is. You think so? All right, we'll see.
90 years.
It's actually
Smart fellow. Actually, that seems to be the consensus. Here, catch.
No, mine's wrong.
Red, okay?
I mean, I don't really show my work, but
Well,
I'll show it this time. I'll show
how
it this
can you
time.
grade it? How can I grade it then?
Well, I showed it on the test.
This isn't a test.
All right. X to the 1 half is X
By the way,
to
that's a
3
pretty good
over
integral symbol
2,
for a rookie.
2.
That's a great.
Yeah.
And then plug it in, so it would be. Oh, I'm gonna explain how I got this. X to the 1/2 or
So that's one of the rules.
plus 1 1/2 plus 1 would be 3 over 2. So then X 3 2 over 3 2 times 2. This is supposed to be a 2, so then it'd be 2/3 times 3 2 2x to 3 over. Okay, I can't really write on this
Okay,
board.
to be honest, we don't need to see all that.
All right, I was just explaining how I got there.
Okay, that's cool.
All right,
Go ahead.
And then 6. Well, you plug in 8. Or no, you plug in 4, which gets 16, and then subtract 2, and you get 14.
Questions? Let's give it up, huh? All right, a couple small things from my perspective. Here, here, here. Other than that, we're good to go. Is everybody good with 4 to the 3/2 power? You can either take the square root of 4 to get 2 and then raise 2 to the 3rd power, or take 4 to the 3rd power and then take the square root. I like to take the square root first if it's a nice pretty number. If this were a 7, I would probably just use my calculator. Okay. Problems? So you're thinking to yourself, there's got to be a catch, right? There isn't. The only thing that's going to change between these two examples and future examples is the difficulty of the antiderivative. Everything else is straightforward. It's the same process over and over again. What's also important is that you you understand what this represents now. Remember we said that that's the area under the curve. So that looks something like, okay, that's a square root function that looks something like this. So we're going from 1 to 4. So that represents the exact area of that region. Okay? Questions? Beautiful. Got another example for you then. I think.
Yes.
There we go. Do that one. Wouldn't be the same without trig. I gave you an easy one. Relax. Just use chain rule.
No.
I can't get you guys are too smart. I tried to fool you.
Wait, is the tangent calculated?
No way! No way! No way!
I just picked this one class you can start quizzes.
But I think on that one I forgot plus.
So obviously it doesn't fit my
Look, he the quiz. I was like,
something wrong. It doesn't matter because pi over 4 is just cosine pi over 4.
Unit circle action for you.
Yeah.
I literally looked at you and I was like,
Oh my god, my second thing of calculus. I thought this was right.
What's the antiderivative of secant squared?
Tan.
Thank you.
Number?
Yeah.
Okay, I got
Okay. I did, but I was just showing you that I was right. I stole it on accident.
Catherine, what's the tangent of pi over 4? No say? 1, correct. What's the tangent of 0? What'd you say? I just didn't hear you. I don't know. 0. Beautiful. 1 minus 0. 1. There you go. Again, there's no trick to this. Okay, or I shouldn't say there's no trick. There's no like, I'm not all of a sudden gonna lull you into a false sense of security and like, bam, try this one. It's the same thing over and over again. Okay. So let's move on to this one. Now, you're freaking out. I know.
Oh, wait, I can do this.
You just,
No,
Hold
no,
on. Wait. Before you hear that?
Yeah. No, we're gonna pretend like we did
It's
it.
a special time in my life. I'm hoping to get chest hair soon.
Wait a minute.
Sorry, was the puberty joke too much? Did I cross a line there?
Too far.
You might be thinking to yourself, self, that's easy. It's just a V. That's not a V. Okay, so this is going to require a little discussion before we do it. On your calculators, please graph that function.
I don't even put in absolute values.
The easiest way to get the absolute value is to go to the catalog down at the bottom, and it's the first selection in the catalog.
What is catalog?
Oh.
Oh, it's a button on here.
Yeah. Right there at the top, ABS.
Cute. Wait, that's actually
Not an automatic break.
This is so awesome.
Wow.
Oh, I love when I actually use my calculator.
On here.
Like, I don't get the first. Okay, I feel like a part
Okay, so before we go on, let's have a little discussion about the absolute value so that you understand how this works. This is not calculus, this is algebra 2, maybe pre-calc discussion. Why does the absolute value graph look like a V? By that I mean, why does the absolute value of X look like a V? Okay, so what does the absolute value do? If you put in a positive number, you get positive. If you put in a negative, you get positive. So what the absolute value graph does, if I start with this function of y equals x, which is that 45-degree line, and I change it into the absolute value of that, it takes the negative values and flips them up. This half is good to go. That's already up. It takes this half and flips it up. Okay, so that's why the absolute value of x looks like a V. So what is the absolute value of this doing? Well, it's taking that graph of x squared minus 2x minus 3, which looks like what? No, the whole thing does. What is x squared minus? It's a parabola. Opens up or down? Opens up, and it's below the x-axis, correct? When I put the absolute value bars around it, it takes anything that's below the x-axis and flips it over. So now, knowing that, you can graph any absolute value graph. So if I give you this, for instance, you could graph that. Graph the cubic function, flip anything that's negative up on top. Well, that's what's happening here. Let me get this mess out of the way. Okay, so it looks like this, and that's what you should see on your calculator. That's 3, that's 1. How do I know that? Because if you set the parabola equal to 0 and factor it, or use the quadratic formula, you get those two answers as zeros. So it took that parabola that was facing up, and it took everything below the x-axis and flipped it up. Okay. Now there's a problem here. I'm looking for the area under the curve from -2 to 3, which means I'm going to go from here all the way over to here. This doesn't matter. In order to do that, I can't just plug and chug into that because I don't know how to take an antiderivative of an absolute value. We're never going to learn that. Nor are we going to learn how to find the derivative of the absolute value. We're going to do it more sneakily, if that's a word. I know that this happens at -1. I'm going to split this problem into two different parts. And this is the turning point. Why is that the turning point? Because that's where the function changes. Does that make sense? Okay. So it turns out to look something like that. Now let me explain that. Here I'm going from -2 to -1. And you'll recall when I was talking about the properties the other day, I said if I'm looking over an integral, sorry, an integral over an interval, I can split it into pieces. Instead of going from A to B, I can go from A to C and then from C to B. I did just that here. So this first part, represented in a lovely shade of blue, is this. Okay. Area under a curve. Now notice the absolute value bars disappear because it's already above the x-axis. This part, in black, is this thing. But you'll notice it looks a little bit different. The reason it looks different is because I had to put a minus sign in there to flip it over the x-axis to get it up on top. I could do that in the beginning or I could do it at the end. Either one, it doesn't matter. It's just going to take the answer and multiply it by -1. Because if I just do this area from the basic parabola, I'm going to get a negative area because it's below the x-axis. But it should be positive because it's above. Okay. Does that make sense? This, the actual process of finding this antiderivative shouldn't be that difficult for you. -1/3 x cubed plus x squared plus 3x, plug in the numbers, you're good to go. Okay, but it's a concept, and more importantly, how to handle that, which is why I chose that problem. Okay? You two got to go?
Yeah.
All right, go.
Wait, so do you take then after you, that's just the whole answer, or do you then take the antiderivative and then plug
Yeah,
it out?
you go and solve the rest of the problem like we did in the previous 2 examples, or 3 examples, however many we did, but I wanted to talk about more of the concept than anything else. Okay? All right, let's keep going because I think I can get a little bit of this in. Bye, guys. You can see the rest of this will be on the video. I'll post it at the end of school. It'll only be like 10 minutes long. Okay. Second fundamental theorem of calculus. We talked already about what happens when you take the derivative of an integral. You go back to the original function, but there's some subtlety that happens here. Notice this is f of t dt going from a to x. This number, a, is always a constant. It has to be in order to apply this function. If that's an x, if that's a t, if that's a y, if it's a variable, this doesn't work.
Will they give you that?
Yeah, they'll give you the number. And in fact, the number doesn't matter. It can be any number in the world, and I'll explain in a second. Okay, so what does this mean? By this, I mean here. Forget about the d dx out in front. What does that little red boxed area mean?
What is the area
Uh-huh.
under that function from x to a?
Correct. From a to x.
Or a to x.
Okay. Everybody good? Yes? So I can rewrite this red part using the first fundamental theorem of calculus as saying f of x minus f of a. Does that make sense? I need some feedback here. Yes or no?
Yeah.
Okay, that's applying the first fundamental theorem of calculus. Now what does that f of a mean? Let's suppose a is 7 in this problem. I take the antiderivative of some function, and then I plug in 7. So do you all see that this guy is going to be some number? That's important. Do you understand that?
Mm-hmm.
We're good?
Yeah.
Everybody? If not, I can explain some more. Are you okay with that?
Yeah.
Or do you need an explanation again? Or are you just going to stare at me?
Can you just explain it?
Sure. If I take this function and I apply the first fundamental theorem of calculus, what we did earlier, I take the antiderivative of f, which is a capital F. I plug in the top number, I plug in the bottom number, and I subtract the two things. Okay? But what we're requiring in this case is that a is a number. So if I plug a number into a function, I get another number. Okay, so we're good, right? Good. Now, I'm going to invoke this little guy. I'm going to take the derivative of this thing.
So after you solve all of it, then you...
Well, you're not going to have to do the work. Just bear with me for a second. You'll see it's actually pretty straightforward and easy. What's the derivative of the antiderivative of x?
The derivative.
Let me rephrase that question. What's the derivative of capital F of x?
Lowercase f of x.
Lowercase f of x. So this is going to go back to f of x. Okay, so we took the derivative of an integral and got back to where we started. What's the derivative of this?
1. If it's a constant.
It's what? 0.
Oh.
So that goes away. Okay. Now, this is the theory part of it. You're not going to have to do that, and I'll explain why in a second. But the fundamental theorem of calculus says when I take the derivative of an integral from a constant to x, I get back to where I started. So I end up back here at f of x. All right, so there's the theory. How does the application work? If I have, that's a little aggressive. Let's not do that one yet. If I have the integral, well, the derivative of the integral from 4 to x of t cubed minus t squared plus 5 dt, what is that going to equal? We're not going to have to find an antiderivative. And I'll tell you, what's going to happen is you're going to see a problem like this. And you're going to dive in and start taking an antiderivative. You don't have to do that. Because notice what happens in this problem. When I go back to all this gunk up on top, the only thing that changed between the left side and the right side is that t's became x's. That's it. Okay. So when I do this, t's become x's. Done. That's it. All that explanation I did in red and blue that I just erased explains why that happens. So what you need to be able to do is recognize that you're dealing with the fundamental theorem of calculus, part 2. In other words, the bottom number is a constant. You've got a variable up on top. Usually these will be t's. Could be z's, could be q's, could be anything other than x. And those variables become x's. Done. Okay? Good. Yes? All right, now how do we change it? What if that's not just x? What if it's some other function? Also easily remedied. The only thing you have to remember in that second part is that you have to chain on the derivative of that guy. Or, even better, just always remember to chain on the derivative of that guy. What is the derivative of x? 1. So I'm chaining on 1 there, which makes no sense whatsoever. But if you do that, it's going to help you when you get to a problem like my board not working. That. Okay, so I've got this. Now, I've got a constant down at the bottom. That's good. I need that. But instead of having x, I've got x squared. So normally what would happen is t's would become x's. If, for instance, this problem said d dx of the integral from 7 to x of the square root of t squared plus 1 dt, that would just be x squared plus 1 square root of the whole thing. Done. This one has a little bit of a snafu here. So t's become x squareds, and we chain on the derivative of that thing inside.
The whole root. You don't just like.
Say again?
So it goes underneath the whole root, not just like attached as a separate like product.
It is attached as a separate product. Notice the root stops there.
Oh, okay.
Yeah, you chain it on the end.
Okay.
This is about 1/10 as important as the first fundamental theorem of calculus. Okay. You're going to be doing definite integrals a lot. This second part pops up occasionally. Okay. And again, t's become the function up on top, chain on the derivative of that function. Would you like to see another one?
Sure.
Okay. I don't think I have one, but I can write one. I do not have one. We'll get to the calculator in a second. Okay, let's try this. We'll do a different color. What is the derivative of the integral from -1 to 2x cubed of, I don't know, the cubic root of t squared plus 4t dt. And again, I'll tell you what's going to happen at some point in time is you're going to forget about this and start trying to figure out how to take the antiderivative of t squared plus 4t to the 1/3 power, and you're going to go insane. Therefore, remember the second fundamental theorem of calculus. Okay. So again, t's become 2x cubes. Chain on the derivative of 2x cubed. So I get the square root of 2x cubed squared plus 4 times 2x cubed times 6x squared. Done.
Wait, do we not put the 3 in front of me? Like the 3 that's in front of me?
Oh, sorry, I forgot that. That's my bad. There you go. Yeah, we're still doing a cubic root. Okay, good? Excellent. Problems? Hot diggity. Okay, let's learn something fun. Let's go here. We'll discard that for now. Let's make that go away. And bust out your calculators. Okay, my calculator does not have a new operating system. So, when I go to math, and then I scroll down, whoa, stop that. Scroll down under math, scrolling, down to FN int, which is math 9, and hit enter, mine looks like that. Does anybody else's look like that?
No.
No? Excellent. So you've all got newer calculators. I'm not even going to deal with this anymore. I'm going to go back to my slideshow. Usually I have one person that has that going on, and I don't want to have to deal with it, so we're good to go. Okay, so let's suppose we want to find the definite integral of some function. So I'll just make one up here. Let's say I want to know from 7 to 14 of the cubic root the square root of x cubed plus e to the x minus 4 dx. Okay. We don't even know how to work with e yet, but I just threw that in there for sauciness. Okay. When you hit math 9 on your calculator, you should get a display. Can I use your calculator for a second? Because I forget what it looks like. You should get a display that looks like this. Yes? Okay. Do I have to explain this? Okay. What's this going to be? What's that going to be? What's that going to be? That ugliness I did over here. What goes there? X. Almost always, for us, you're going to put an X in there. And then you hit enter, and it does a bunch of fancy stuff behind the scenes, which you don't care about, and spits out the answer. Get an answer? Okay. Square root of x cubed plus e to the x plus 4. Can somebody confirm 244.882?
I got 469.2.
Uh-oh.
Where's E?
You do wrong, so I think-
Oh, it's not the square root over the whole thing. It's just the...
Where's E?
Notice the square root ends here.
Oh.
Okay.
Oh, sorry, I couldn't really see. Wait, yeah, where's E?
400... Dexter, you said 469.283?
Yes.
Hot diggity.
Nice.
Okay. Questions? Yes.
Are we gonna get to like trapezoid rule and symmetry rule before?
Yeah, later. All right, the last thing, we'll pick up with this tomorrow because this is another important idea, which is the area accumulator. Hang your chairs, please, and unlock your tables for me. I would greatly appreciate it.